Alright, so I took the emails that were sent to me and put together a review video that covers what the students had asked for, as well as a couple of extra things that I thought we needed to cover. Of course, if you're watching this and there are certain things that you don't feel like you need to review, you can always fast forward and skip the sections you don't need and just fast forward to the part that you feel like you do need instead. I do recommend that everyone at least looks through the when to use which formula part, which will be toward the end of this video. I did also try to put a lot of this stuff in the order of which it was covered. That way if we're referring back to things that we can. And so for each thing I will also refer to which set of notes to look through to help you review even further some of these ideas. So first we have the normal curve rule, which of course is covered in the normals notes, which was the very first set of notes that we covered back in week 1. So if you're needing to go back and review any of the normal stuff, watching your week 1 videos, all of the weekly emails are still out on Blackboard with the links to each of the videos out there as well. The specific thing asked for from the normals notes was looking at the normal curve rule. So first we're going to review the rule and then see how it applies to problems. So the overall idea of the normal curve rule has to do with that 68, 95, 99.7. And in this set of notes we drew two different pictures, so I'm going to go ahead and redraw them both here. So if we remember, the normal curve is always centered at the population mean. And then we go out up to 3 standard deviations away in both directions. So we're going to kind of go over that sigma was that standard deviation that we went over each time. And so mathematically here along the bottom, this would be mu minus 1 sigma, this was mu minus 2 sigma, and then this is mu minus 3 sigma. On the other side, we're just adding instead of subtracting, but otherwise the numbers are staying the same. And then when I did that, if I went out the 1 standard deviation in either direction, I would get 68% of my data. If I went out 2 standard deviations in either direction, I get 95% of my data. And if I go out 3 standard deviations in either direction, we get 99.7% of our data. So then what we did with this curve is we took the same curve, same numbers along the bottom, so let me kind of quickly add those here. And then what we did instead was broke things up into all these different pieces. And figured out how much had to be in each piece. Well, we know if we went out 1 standard deviation either direction, we would get 68% of the data. And then I have 2 different spots here to put it in. Since our graph is symmetric, we split that 68% up equally. So I took my 68% and divided by that by 2 to get the 34% that would be in each of those pieces. But then I also know that between here and here is 95% of my data. But now if I look at my picture, I already have part of that covered. I have 68% of it already on there. So I subtracted off how much I already have. So I have 27% left to add to my picture. 2 different places to put it in, which again are equal in nature since we are symmetric. So I took my 27% and divided that by 2 to get that in each of these pieces all have 13.5%. Then if I went out the 3 standard deviations, we know we get 99.7%. Just looking at like the other one, I look at how much I've already put on my picture, so I have all of those 4 pieces that I need to worry about, which add up to the 95% that I was working with. So I'm going to subtract 95% leaving me with 4.7%. Again, 2 places to put it in. So I'm going to take that 4.7 and divide it by 2 to get that there's going to be 2.35% in each of those pieces. And then last, which might not seem like we have it covered, are these little pieces out here on the ends. Right, there's still data that's out there. I've just got to figure out how much. Well, we know the total picture should add up to 100%, so I should cover everything. We've already put on 99.7%, so there's only 0.3% left to put on the picture, and again 2 spots to put it in, and so there's going to be a 0.15% in this little tail and a 0.15% in that little tail. So again, that's just a review of the rule. Now, how does that actually apply to some problems? So let's look for an example where we're going to do this with multiple ones. So we're looking at apartment rent in northern Kentucky. We're told that our mean is $545 and our standard deviation is $65. We're using the normal curve rule only. What is the probability that a 1-bedroom will cost less than $480? So I'm just going to start by drawing the picture. It's pretty hard to do a lot of these normal curve ones without drawing the picture. So I have my 545 here. And then I'm going to do is sort of look for going out and increment my standard deviation and seeing if I kind of find this number. So let's start by going 1 standard deviation out in either direction. So I'm going to go 65 to the left and 65 to the right. And I get 480 and 610. Well, I've already hit the number in my problem, so I don't really need to worry about going out any further. So let's just work from this picture and figure out what we know. Well, so far, I didn't do the greatest job drawing that picture. Let me fix that real quick so it's a little bit better. That way it was a little bit more symmetric looking. So if I go out that 1 standard deviation either direction, I know from up here that that's 68%. And I don't need to worry about going out like doing the 95 or 99.7. Let me just work with what I have. So I already have 68% on my picture, and I have 2 spots left. How much do I have left to put on there? Well, there should be 100% in total. I've already put on 68%. So I have 32% left to add. 2 spots to put it in. So that means I'm going to have 16% here and 16% here. Now, what do we actually want from the problem? We want the product that's less than 480. So where is less than 480? Well, it's just that piece. So what's my answer? So there's a 16% probability. So that is our probability that a 1-bedroom in northern Kentucky costs less than the $480. Alright, another example with the same setup. So this one we want to find the products between 415 and 610. So again, I'm going to start with my picture. My mean was 545. And then again, I'm going to kind of start going out in my increments here. So if I go out 65, I get 480 and 610. So I've already hit on the right hand side the 610, that's my number there. But I haven't hit the 415. So I'm going to go out another one that way. And then just make sure things are balanced, I'll go ahead and go out another one that way. And then we can figure out what we actually want. So this is going to be 415. This will be 675. Alright, so what we actually want between the 415 and that's 610. Alright, so let's figure out what we know. Alright, so we know, again, between that 480 and 610, that's our one standard deviation out. So I got 68% there. So the only thing I really need to do is find this little piece. Okay, how am I going to do that? Well, again, I know if I go between here and here, that should be 95%. I've already put 68% on my picture. So I have 27% left to add to the picture. But again, I got to worry about putting it in both spots. Sorry, 27% divided by 2. So I get 13.5% will be in this piece and in this piece. But what do I actually want from the problem? Well, I want between 415 and 610. So I want this piece and that piece. So we're just going to add together the 68% and that 13.5% to get 81.5% probability that a randomly selected one bedroom in northern Kentucky costs between $415 and $610. But probably that one bedroom costs more than $545. Well, that's my actual mean. So, and I want more than 545. So if I draw that line right there, how much is on either side? Alright, there's 100% total. It's symmetric. So they gotta have an equal amount in each spot. So there's gonna be 50% on this side, 50% on that side. I want them more than, so we're just going to get 50% as our answer. Alright, last one of these, we're going to find probably that it costs between $545 and $675. So again, going out my increments here, so 480, 415, 610, 675, so I get my numbers. So let's figure out again what we do know. So between here and here, so we're 2 standard deviations out, is 95% in total. But I want just this piece of it. So if there's 95% total between it, how much is there in each of those pieces? Well, I'll just take my 95%. It's got to be equal because it's symmetric. So to get that 95%, there's 47.5% here and 47.5% here. So our answer would be a 47.5% probability that a one bedroom in northern Kentucky costs between $545 and $675. Alright, so that ends the normal curve rule part of it. If you have questions on any of that, or if you need to go back and review some of the other stuff from the normals, again, that's from the week 1 material. Feel free to rewatch those videos or drop me emails about that material. Next, one of the questions I was asked to look at was reminding ourselves the difference between quantitative and categorical data. So this, information-wise, came from the who, what, when notes. So that was week 2. for a lot of the definitions and type stuff was covered within that set of notes. So first, just remind ourselves the difference between a categorical and a quantitative variable. So a quantitative variable is going to be numeric, but it also had to quantify something, versus a categorical variable that the responses consisted of categories. And all this might seem something that some of us aren't struggling with, but this also goes back to figuring out when we're using which formula. So you're going to hear me stressing this part when we get to the how do we pick which formula to use as well. So feeling comfortable with this is an important part of feeling comfortable with what formula you're going to be using as well. So just kind of first as a reminder, that and quantify part was important, because one of the examples I gave was like your area code. Your area code for your phone number is a number, but it does not quantify. It actually tells you geographic location instead. So area code is really a categorical variable. So I gave some examples here for us to think through which variable type they are. So for course letter grade, you're given an A or a B or a C or a D. What kind of variable would that be? So that's going to be a categorical variable. How much mileage per gallon do you get? So if I were to ask you that question, what kind of answer would you give me? Okay, it's going to be a number. Does it actually quantify something? So if I get 30 miles a gallon and you get 33 miles per gallon, does that difference of 3 mean something quantitatively? Yes, you get 3 more miles per gallon than me, right? That number means something to me. So that's going to be a quantitative variable. Your U.S. Army rank. So are you a colonel? Are you a general? So that one would be categorical. Your favorite color. Again, think about what kind of answers you're going to give. So that's categorical. How fast you run a mile. Mile run time. So you're going to give me a number, and again, does that difference mean something? So if I run a 10-minute mile and you run an 8-minute mile, you're running it 2 minutes faster than me, right? That number does actually mean something to me. And then our diamond carat weight. So if you have a half a carat diamond versus a 1 carat diamond, do those numbers again quantify something with that difference? Yes, it does. Right? So you have twice as big of a diamond if you have a 1 carat versus a half carat diamond. Right, so again, some tricks to think about when we're trying to decide that is to keep in mind if you were being asked the question. So in a sense, kind of ask the question of yourself is one thing to do. So kind of think about how would I actually respond if this was something that was asked of me. Because again, as a reminder, a variable is on an individual basis. And sometimes we get confused on if I say, you know, from our 1,000 people, we found that 80 of them were this major. And we see those numbers, and so we automatically think of it as being quantitative. But if I'm asking you for your major is categorical, right? So it doesn't matter what, we can use numbers to summarize both types of variables, but that doesn't mean that the individual thing is always numbers that we're working with. So one question is to ask the question of yourself. The other thing is to actually look for some sort of keywords in the problem. A lot of times, if you see that word mean showing up, you're working with something that's quantitative, because we only calculate a mean for a quantitative variable. Or if you happen to see something that says out of, generally you're going to be working with something that's categorical instead. We're kind of counting how many people are in each group. So that idea that groups makes us think categorical as well. I'll give you some other tricks to think about when we're trying to figure out which formula to use as well. Right, next I was asked to look at histograms and summary statistics and how those relate to shape and those different types of things as well. So first, I was going to focus on how you can look at the numbers to determine the shape of your graph. And when we're talking about looking at numbers to determine shape, so we can use the mean and the median to help us choose the following options. So we can decide if it seems pretty symmetric, if it's skewed left, or if it's skewed right. From the numbers alone, we can't tell anything about if it's unimodal or bimodal or anything like that. That part has to come from the graph itself. We can't get that from the numbers. So how do we look at shape for the numbers we have here? So I did give an example of each here. So what we see here with the first graph is we have a skewed to the right graph. This number's kind of like which way you slide off is the way that it's skewed. So the majority of data is on the left, means we're actually skewed right. If we're skewed right, your mean is going to be bigger than your median, because those higher numbers, since we use every number in the calculation of the mean, kind of pull that mean up in that direction. So think about if I'm looking at numbers between 0 and 20-ish here. If I throw in the number 1 million, that's going to have a huge effect on that mean, and it's going to get pulled way up in that direction here. The second graph I have is more of a skew to left graph. Again, majority of data on the right, we would slide off to the left here. If we look at their mean and median, what you see is the mean will actually be less than the median here. Last, I gave a symmetric graph, and I didn't give you one that was actually unimodal. I wanted you to see a different looking symmetric graph, so you get to see something a little bit different. So if that were balanced in around that middle spot, so when because of the idea of balance and these sort of offsetting those, these offset those, these offset those, we balance out for both the mean and the median right smack dab in the middle, which is why your mean and median will be exactly the same if it's perfectly symmetric, but it will also be really close to the same if it's relatively symmetric. So if it's symmetric, the mean and median should be pretty close to each other. The other question relating to matching summary statistics to the graph like you had to on your last exam was trying to figure out with those two symmetric graphs I gave you of how do you know which output goes with which. So this is where standard deviation is important. So if you remember what standard deviation is, it's the typical distance a point falls from the mean the first thing I want to look at is where the mean actually is. So, right, the mean on this one is 6, so it's right here. And I'm trying to look at how much data do I have close to the mean versus how much data do I have far away from the mean. So in this example, I have very little data right here at the mean, but a large amount of data that's very far away from my mean. So the fact that I have a lot of data far from my mean is going to result in a larger standard deviation than, say, a graph that has more of the data right on the mean and less data further away. So as this graph has the same mean and median as our last graph, but this 2.449 standard deviation is smaller than what we had in our previous example of this 3.162. So the more data that's further from the mean means you're going to get a larger standard deviation. Alright, so again, this is kind of as a quick summary on that. You can look at the mean and median to determine if it's symmetric, skewed left, or skewed right. If it is symmetric, again, the mean and median won't always be exactly the same, but it should be relatively close. One thing you can use that for when you're trying to determine your own shape is if you're kind of in between things. Maybe there's a graph that you can't quite tell if it seems very symmetric versus it's slightly skewed one direction. So if I'm unsure by looking at the initial plot itself, I can look at my summary statistics to help me figure out, well, how skewed really is that graph? Is it anything I really need to worry about, or is it pretty symmetric instead? We like symmetric graphs because then the mean and median are close enough that it doesn't really matter if we look at the mean or the median. For the standard deviation, this deviation is looking at where we are relative to the mean. So the more data that's further away from the mean, the higher the standard deviation is going to be. So for example, if I gave you an exam average and said the exam average is 75, that's really not enough information for you to know how students did. If we had a standard deviation of 5%, kind of think about what I know from Chebyshev's rule, right? So if I'm 75% is my mean, and I go, I'm going to write this down so I'm not talking too much. If that was our mean, and 5% was our standard deviation, we would know if we went out, 2 standard deviations, let's say, so we're going to get 65% to 85%, that at least 75% of the students scored between a 65 and an 85. But if instead you had a mean of 75% and a standard deviation of 10%, now if I go out 2 standard deviations, I'm much more spread out. Which kind of tells me that means that my data is a little bit more spread out as well. The data isn't as close together. So in that idea, this one, more students are going to score closer to that 75 than in this example. So here there's more students that are scoring both lower and higher than the mean than there was in this example. And again, if something isn't making sense or you need more information, you can always go back to that week's videos or drop me emails with some specific questions and I can answer further. The next thing I was asked to cover was how do you know when you should do a confidence interval versus a hypothesis test, like where you had to circle the right answer on the previous exam or that multiple choice of which one should you do. So thinking through the big differences between the two. So a confidence interval, the main goal is an estimation. So I don't know what a number is, I want to estimate it. So maybe I want to figure out, well, what percent of students pass Stat 205? I just want to know what that number actually is. Hypothesis testing, you have something about a decision that you want to make. Does at least 75% of students pass 205? I have an actual decision I want to make. I'm not just trying to figure out what that number actually is, but I'm actually trying to make a decision between those two things. So the idea for that as well, for a hypothesis test, your alternative hypothesis is your goal. Right, you have some idea, okay, do at least 75% of students pass 205? I have some goal that I actually want to show. With confidence intervals, the goal is really just to get the number. So I might just want to know, well, what percent of people are okay with bringing in the Syrian refugees right now? I'm not making a decision about that number. I just want to figure out, well, what percent of people are in favor of that? Does that number look good is a different decision, right? If I were to ask, does a majority of the United States citizens believe we should bring in the Syrian refugees? That's a different question. I just want to know what the number is or have a specific decision that I actually want to make. So it's kind of two different ideas that we have here. So when you're reading through a question, that's what kind of the big thing that you want to ask yourself. Do you need numbers to answer that question? So if I say, I want to figure out what percent of American citizens are okay with bringing in the Syrian refugees, you need to give me numbers to help answer my question. That's what I need. First, when I do a hypothesis test, I'm looking for some type of yes or no decision. Does a majority of U.S. citizens believe we should bring in the Syrian refugees? Yes, a majority does, or no, a majority doesn't, right? I mean, that's what I want a decision between those two things. that's how I should make a decision on when I should do a confidence interval versus a hypothesis test, is depending upon what my goal really is with the problem. Generally, in the actual problems on a test, I will pretty much tell you which one to do, so you'll see, test the appropriate hypothesis test with a 5% significance level, or estimate the mean value with 95% confidence. So a lot of times you'll see those actual numbers in the real problems as well. Alright, the next main thing I wanted to go over, because I know this is where some students struggle on the final, is when do I use which formula? And again, so next to each of these boxes, so these are the same formulas that are on your formula sheet. I just had to organize them a little bit different number of pages wise to make sure that I have room to take notes on it here, and since I formatted it landscape instead, so I could draw a little bit better. So, but again, and against each one, we'll put which set of notes it's from, so you can reference that as well. So when do I use this very first formula that involves the normal distribution? So when do I want to use that? Well, for this, it had to say the word normal somewhere in the problem. That has to be true. And we have to be talking about an individual. So if it makes it a little bit easier, you can think of that as having a sample size of 1. So if you go back and read all of the normals notes, or go back and look at that stuff, what you'll see is it'll say, what's the probability A randomly selected woman? What's the probability that A house falls between these two prices? There's always that an individual nature that's going on inside for that formula. The next two sort of go hand in hand. They're both the idea of sampling distributions. One's of the proportion and one is of the mean. Whenever I see that word proportion, that's going to refer to a categorical variable. Whenever I see a mean, that's referring to a quantitative variable. And these will generally stand out pretty easily as well. Generally, there's going to be something about finding the sampling distribution in the problem itself. Not always, because that's a pretty big key to know that you're working with that. So if you see that word sampling distribution, and keep in mind that you have these names on the side of your formula sheet as well. So you still see those words of sampling distribution on the side. Which of each set of notes these came from? So the sample distribution of a proportion came from the 1 categorical variable part 1 notes, which was week 3. And the sample distribution of the mean came from the 1 quantitative variable part 1 notes, which was week 9. So if you see that word sample distribution in the problem, the next decision you have to make is if it's a categorical variable or a quantitative variable. So if I want to find the sampling distribution that involve looking at majors of students, okay, it's a categorical variable, so I'm going to be following this type of pattern over here. If instead I'm trying to find the sampling distribution that involves the exam scores of students, quantitative variables, I'm going to be looking at the quantitative, the mean one instead. Other tricks you can think of with this is with quantitative data, we have to be given a standard deviation. So there's that symbol, which is an extra symbol that I don't have when I work with categorical data. This bottom number was our new standard deviation, that standard error that we would create, but we actually had to calculate that number. It wasn't given to us in the problem. So that's one thing that we can do is generally if you're given a standard deviation in some way, you know you're working with a quantitative variable. So it's one of the little test-taking tricks to help you with that as well. Then the majority of our other formulas look at the hypothesis testing and confidence intervals that we did. And they're broken in to pieces. So the first main chunk is for proportions of one sample. So what that will mean is that we are working with one categorical variable. This is going to be both the part 2 and 3 notes. More specifically, the hypothesis testing came from part 2, and the confidence intervals came from the part 3 notes to go along with that. The sample size also came from the part 3 notes, kind of like tie each one together there. So those were covered in weeks 5 and 6. Alright, so how do I know I'm working from this box? So the first thing I need to have one variable. I need that variable to be categorical. If it's quantitative, I'm doing something different instead. And I need to either be doing a confidence interval, a hypothesis test, or finding sample size. If that's one of my 3 goals, this is where I'm going to be. The next main chunk of the formula sheet is mean of one sample. So again, we're still going to have just one variable. Since it's a mean, we are looking at quantitative variables. Note-wise, this is just part 2. We crammed all of hypothesis testing and confidence intervals for quantitative data into 1 week, since we had already covered the ideas of those. And that was covered in week 10. Alright, so how do you know that you're here? Again, you're only going to have one variable that you're looking at. This time, it's going to be quantitative. And again, you're either going to be doing a confidence interval, a hypothesis test, or finding sample size. Alright, the next chunk of the formula sheet, so I think now we're on the back of your actual formula sheet, involves the dependent or paired samples and the independent samples. So these two are covered in the same set of notes. That was our comparing a quantitative variable in 2 groups notes. Which was week 11. So both the independent and dependent is covered in there. The first part of that notes talked about how to make the decision between independent versus paired. Once you make that decision, you know which of these 2 boxes, main boxes, that you should be in here. So how do we know when we're in this area? We are going to have one quantitative variable. We will also have one categorical variable that has only 2 categories. So that's where that idea of comparing in 2 groups starts. So if we're comparing 2 groups, we have this categorical variable that's comparing 2 things. So our opening example, we might have looking at how much ice cream was put in a medium versus a large bowl. So I have the amount of ice cream, which was quantitative, and then I had bowl size, which was either medium or large, only 2 options. So I know I'm going to be somewhere in one of these 2. then I actually have to go to the sample. So how sample was taken determines if you're independent or paired. No matter what, whether you're independent or paired, the goal is always comparing things. Just because I wanted to compare things doesn't mean that my data itself is actually paired. It goes back to, again, how the sample was taken. That's the important part here, how the sample was taken. So we also have to go back and look at our data to say, okay, do these two things have to go together or not? So if I take a random sample of 20 guys, a random sample of 20 girls, is there a certain guy I have to match with a certain girl? That's the kind of questions I want to be asking myself. And if you remember from back then, we always assume independent until we know otherwise. So if there is no reason to pair them, we're going to assume that they are independent. Now if I sampled 20 men and then I sampled their 20 wives, okay, a certain husband goes with a certain wife, so therefore it's going to be a paired sample. So again, that one boils down to how the sample itself was taken. Our next box here, the 3 or more independent samples. We didn't cover paired or dependent for this option. This one came from the ANOVA notes, which was week 12. Sorry, week 13. So we had a test in the middle there. From week 13. Alright, how that one you know, this is still one quantitative variable. It is also going to have one categorical variable, but now that categorical variable has 3 or more categories to it. So on one of your quizzes, you were asked to compare the 4 different types of positions that I had on their batting average. So we had the batting average, which was quantitative. We had the position, the primary position, is what we called it there. And it was either infield, outfield, catcher, or pitcher. So there's 4 different options there. So that's why we would be doing the ANOVA for that one. This one's always going to be independent. We still might need to address as one of the conditions why they're independent, but if they were to happen to be dependent, we have not talked about how to cover that material. Alright, the last spots here on our formula sheet. So we have the 2 categorical variables, so that's actually been longer ago. So this was the comparing 2 categorical variables, just as it sort of says right there. And that would be from week 7 material. So that was on test 2. How you know you're there is very simply that we have 2 categorical variables. So if I want to see if there's a relationship between gender and what your letter course grade is, that's going to give me this chi-square test, the 2 categorical variables. That's been a little while since we've done that material, so where we calculate like the row percentages and the expected counts. And then last we have the material that's most recent, the relationship between the 2 quantitative variables. Those are comparing 2 quantitative variables. Which would be week 14. And again, how you would know there, you have 2 quantitative variables. So maybe I want to see if I can predict the ticket price for a Bengals game based upon how many wins the team currently has. So number of wins would be quantitative, ticket price is also quantitative. So that's why I would be doing the regression material there. Alright, finally, one of the other questions I was asked to look at was when to use what terminology. I kind of know that some of that can be confusing, and the main things that were showing up for this person that asked was the idea of like when do I use mean versus when do I use typical, and those different types of things there as well. So the idea of talking about typical was, first of all, way back when in the who, what, when notes. And this is when we were looking at individuals. And it was a quantitative variable. So I might say, well, the typical student scores between this and this on the test. But again, it's on an individual aspect instead. Versus the word mean or the word average, which really do mean the same thing, is when we're talking now about a group. So you're going to have an n bigger than 1 at this point. And it's also working with something quantitative. So the big idea with mean is you need to be working with a group. There are other times that didn't initially use the word typical, but we did not use the word mean or average. So we don't want to use the word mean when we're using Chebyshev's rule. Because there we were looking at individual values, so we don't want to use the word mean there. We also didn't want to use the word mean in the most recent videos when we talked about a prediction interval. Because a prediction interval, again, is for an individual. Whereas I did use the word mean in that set of notes when I would work with the confidence interval, because that was the distinction between the confidence and the prediction interval. Was we talking about everybody, the mean of everybody, versus an individual. So again, that idea is, you know, maybe I would like to know, well, what's the mean exam score for my students? But you would like to know more of, okay, how am I going to do on the test? Right, so that goal of a difference of a confidence interval versus a prediction interval does mean that the calculation is done differently. So it does result in different numbers. That's why we want to be careful of when we actually do use the word mean, that it should be there. You should also never use the word mean when you are working with categorical responses. Only. And I'm going to emphasize that only part here. So when we did ANOVA, which was back here on the previous page, we still are talking about a mean, but we do have something that's quantitative that we're working with here. But I never want to use the word mean when I'm solely working on categorical data. It's like when I'm working with this proportion stuff, the word mean should not be showing up there at all. Or when I'm doing the very last, the 2 categorical variables, the word mean isn't showing up there either. Right, so those are the main things I was asked to cover. This might trigger some extra questions that you may have for me. So please drop me emails. I can try to set up individual WebEx sessions with you if we need to meet more face-to-face. Again, you're always more than welcome to come to my face-to-face office hours, or we can set up an appointment here if that's better for you. But you do have to let me know if you have questions on things as well.